In the last simulation, we have seen a cosine function, and we saw the cosine function is represented by a plus b cos cx plus g. There are four parameters, constants a, b, c, and g. Now in this simulation, let us extend that concept and apply it to a wave. It is important to look at closely because a wave has two cosine functions that we will see. But just before going ahead, let us refresh what was said in the last simulation. He said it has four parameters. This represents a simple cosine function. If you change A, it shifts the entire graph. So it is known as a DC shift. If you change B, it affects the height of the graph, and it is referred to as amplitude. And C, if we change C, number of cycles in a unit length changes, and that is referred to as frequency. And G, if you change G, the graph appears to shift in one direction. It is known as initial phase. It affects where the cosine graph will start at 0 of the independent axis. So in today's simulation, let us look at a wave and understand cosine functions associated with visualizing a wave. So as I said, there will be two cosine functions for a wave. If on the x-axis, if it's a spatial coordinate, then the y-axis represents the displacement of all the particles at a given time from their mean position. This is one such graph. If this is a rope, and this is a spatial coordinate, this is at a one instant of time, and this says that each particle is displaced from the initial position by its own amount. So this leads to a cosine graph in space. Now there's another cosine graph in time, because wave has two independent parameters, space parameter and time parameter. So we remember the equation comes like cos kx plus minus omega t. So within the phase, there's a kx and omega t. So at a given space point, how the motion of a single particle looks. This was shown in my first video on waves, where one particle was chosen. Here also we will choose one particle and trace its motion as a function of time. So for that, let us choose one particle. Also remember this phase point, it's starting right on 7. So now we see the wave is moving. Now I have not put any speed because speed is not that important in the simulation. Also I have not put at what time it is. So the time is passing and the wave is moving towards right with some speed. So look at this. This cosine graph has, at each instant of time, it is a cosine function, but it is shifted. Now in this graph, where x-axis is time, now y-axis is one of the particles displacement, which is this. It is going from -7, here it is minus, it goes up, +7, it comes here, again it comes to -7. Now remember, this is not moving, it is stationary, because it's not a wave, it is pertaining to a single particle, how its position changes as a function of time. So let us observe, it will the display will show up to 1 second. This is time in seconds for 1 second. So we can see it is a cosine graph in time. Also in textbooks, cosine graph comes as a plane wave solution for the differential equation. So the 1 second is over, and now we have two cosine graphs. This is cosine graph at end of time. The time is not displayed, as I said. And this is cosine graph of this particle as a function of time for a period of 1 second. Now there are two important things when we deal with functions, cosine or otherwise. To tell what is the equation, looking at the graph, and looking at the equation, tell how the graphs look like. For example, let us look at this. This says 7 cos 4x plus 0. So this 0 was initially actually. So let us understand for 7. 7, it is because oscillating between -7 and 7. So I have 7 is amplitude. 4, because there are 4 cycles in 2 pi units of x. And let us look at the phase. Phase was initial phase. So it's around 6. So let's use the slider and get it. No, it has to be other way. Something like this. Somewhere here. So this is 7 cos 4x plus 0.376 is this graph equation. So let us look at the parameters associated with it. The first parameter is period. That is, what is the distance between two adjacent points which differ by a phase of 2 pi, or to simply put, what is the distance between two maxima or minima, because that is they are separated by a phase of 2 pi and it is easy to locate. That's why textbooks always talk of peak to peak or a minimum to minimum. So 1.5708. For example, here it is 10.1 and it is about 8.4 or 8.3. So that comes out to be 1.6. So 1.6 units of x-axis is period. So in 1 unit, that is, this is 1 unit, there are 0.6 of oscillations. So 1 unit is somewhere here. You can see it is less than a half. So it is like if it is space coordinate, it will be per meter. So this period is referred to as wavelength. If x-axis is space coordinate, this is spatial frequency. And also there is another quantity of interest. This is in 2 pi units, because remember there is a connection between a circular motion and a sine graph. A one complete motion of a circle leads to one sinusoidal cycle. So that's why in 2 pi radians, how much? So we have already seen in 2 pi radians, it is 4 cycles. That is 6.28 is somewhere here. So you can see 1, 2, 3, and 4. So now let us look at the graph of this, and also 2 pi, this is magnitude of 2 pi by lambda, the wave vector. Now if you come to time graph, time versus displacement of one of the particles. So let us see what is this period. The period is, it is less, it is very small. So first let us count how many cycles are there. So in 1 unit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and about 12. So in 1 unit of time, there are 12 oscillations. So in 2 pi units, it will be about 74 point or 75. There will be 75 cycles. So period will come out to be 1 by 12. So in 1 unit, there are 11.9 cycles. And in 2 pi units, so there are 75, and between two adjacent minima, the time is 0.08 seconds. So when x-axis is time, this period will be referred to as time period. And in 1 unit of time, it is referred to as frequency. Generally, it is referred to written as a symbol mu. And in 2 pi units, it is omega, 2 pi mu. It is radians per second. So that's all for today's visualization. So important point is a visualization of a wave generally has two cosine functions associated with it, and we should be careful in looking what is on the x-axis, whether it is a space coordinate or time coordinate. But nevertheless, the quantities of interest will be derived in same way, but either it will be length or time, or 1 by length or 1 by time. Thank you for watching.